Good morning, ladies and gentlemen. My name is John Lloyd. I am best known in this country as a comedy producer, shows like Blackadder and Spitting Image and QI. But I also have another job, an academic job. I am the Professor of Ignorance at Southampton Solent University. Thank you very much. My sole job is to know that I know nothing. And one of the things I don't know is what on earth I'm doing here, talking to this august gentleman, as I'm sure you all know, Professor Sir Andre Geim, winner of the 2010 Nobel Physics Prize. So, Andre, let's start at the beginning. You were born in Sochi on the Black Sea, and I read that your best friend until you went to university was your grandmother.
Yes, that's true. With respect to Sochi, because of Russian origin and accent as well, people sometimes when it snows in Britain or in Europe, people say, "Oh, you must love this." And until the age of 20, I have never seen any snow because it's kind of not snowing. Only when I moved to Moscow to get my education, I saw the real snow and really hated my 10 or 15 years in Moscow. But otherwise, Sochi, although it's actually Winter Olympics were there, but those Winter Olympics were very fine, the mountains, and on the sea coast it's just Mediterranean climate. It's probably one of those stories tells you how it's dangerous to generalize your knowledge from a general perspective you get from newspapers and etc. for the whole big country or big population.
So one of the things I really like about reading about the research you were doing then is that Andre had these things called Friday night experiments where they would do stuff for fun, silly stuff, which produced some quite interesting ideas, didn't it? Were you the first person to come across the idea of Gecko tape?
Yes.
I mean, that is extraordinary because you were years ahead of your time, decades probably.
It came later.
Do you all know about Gecko tape? You come across this?
Let me show.
He's going to hang from the ceiling now.
Yeah. Can you please switch on? Yeah. Actually, it was later. In order to have these Friday night experiments, you have to be rather relaxed, and relaxation comes when you get a permanent position. When you get a permanent position, and at that time it was at the University of Nijmegen in the Netherlands, you start thinking, okay, I'm as a scientist probably not paid enough, as John pointed out yesterday during our dinner in a restaurant, okay? So at how little scientists are paid, he said, okay? So you're thinking you should at least have fun. And fun is not going to a well-trodden path, but to do something for your soul. And I came across, okay, it was one of those strange things I came across with the paper which explains this amazing climbing ability of geckos. And I read from other papers what it is about, and I was shocked how simple mechanism is behind. Okay, essentially toes of geckos are covered with tiny hairs, and if you take a pen, a hair, and touch whatever you touch, there is a minute force which acts between two surfaces. So your hair would attach to, say, table. It's like atomic force microscope. Anyone who uses it, they know that the tip it's attracted. It's all nanonewtons, but geckos utilize those nanonewtons, put in a billion hairs working together. So essentially, a billion multiplied by nanonewton, and it gives you quite a formidable force and so on. And when I thought about this. It's the same science we were dealing in our laboratory, so we can mimic what can be done. Okay, so we mimicked at that time. That's how artificial gecko hairs looked like. So I wanted to make a glove. It was nearly 15 years ago. And put one of my students out of a window, okay, the naughtiest one, okay, they were to show that it's possible, okay, whatever it is. There was no lack of students, but we managed to produce only a tiny bit of gecko tape, 1 centimeter, so I have to limit myself showing proof of principle that it's possible, and the progress in this direction is relatively slow. It's a very highly cited paper, something like 1,000 citations, people working intensively. I have seen people hanging, real people hanging from the ceiling using this kind of technology, but the problem is after you detach, you have to attach again, and reproducibility. Geckos are smarter, nature is smarter. They self-cleanse their hairs for each attachment. We can't do it now.
Do you have a slide of magnetic water as well? That was another thing that I'd...
Yeah, okay.
Does anyone know magnetic water? Anyone come across this? Fascinating.
So that's what I call very random experiments, okay? So as I told, I was looking for something out of an ordinary path. I was doing mesoscopic superconductivity. Doesn't tell you much about this, but we had these huge facilities around which consumed a lot of energy and required cryostats to do my professional experiments. So I thought, okay, why wouldn't we pour water? What happens with water in very high magnetic fields? Somewhere at the back of my mind there was a knowledge that something strange happening with water. There is allegedly, when you put a magnet on your tap, there is no more scale on your kettle. Sometimes it works, sometimes it doesn't, so I can't contribute professionally into this subject. I still do not understand whether it works or not, but the idea was behind. So once upon a time I just pour water inside the magnet. That's what not professionals normally do. They don't pour water on top of their expensive equipment, and actually I didn't expect much. I expect that water would end up on the floor. Instead of that, we saw something like this. It's in this case it's a tennis ball of water which levitates somewhere near the top of the magnet, and we push air in order make it not static, and it's a beautiful picture. It took me half an hour to realize that the phenomena behind is just diamagnetism, and no scientific discovery, no gravity, anti-gravity or something like that. The phenomena was known for 125 years by that time, but it was a break down of our perceptions that diamagnetism is a weak phenomena in magnetic fields which comparable to fields which you experience if you go to hospital and have magnetic imaging scan. This kind of magnetic fields can cancel gravity. So, but you see, it's very therapeutic experiments, and how it was. I like watching these movements. It's calmed down you quite well. But my colleagues didn't believe me. We had a queue of different people coming around saying, "Okay, it's all hoax. It can't be." From people who professionally worked all their lives with this kind of facilities. Those facilities were for 30, 40, 50 years in many places around the world, and no one did these simple things like pouring water inside. And brilliant ideas came from my Dutch colleagues. They suggested to put beer, cheese, all sorts of vegetables, and so on. So at a certain time, it has become obvious that you need to make a symbol of this diamagnetism, and after a lot of tries we found that the best symbol would be something living creature. This is a small frog, and we managed even to make a few seconds of movie out of this. This was a big hype for some kind of I don't want to show this.
So as a result of this particular experiment, Andre is the only individual person in the world to have won both a Nobel Prize and an Ig Nobel Prize.
Aren't I proud
cool,
of both of those? Yeah. Okay, yeah. Well, this material, I have a slide, okay, this material, okay, have a lot of superlatives. I gave up with making the list, okay, quite a few years ago. Of course, it's a thinnest imaginable material. As I say, 1 gram enough to cover a football pitch. It's the strongest ever measured because there are no defects and the bond is very strong. It's the stiffest material. It's stiffer than diamond. At the same time, try to stretch diamond. Diamond would crack, and graphene is 20% elastically stretchable, a little bit like rubber. It's also highly pliable material as well. You can bend it and turn it around and do knots with this one. Outperforming diamonds in terms of conductivity. It allows current density thousands, probably even million times more than copper allows. So the list goes on and on and on and on. And I gave up with making this list in 2009.
Well, I mean, the applications and potential applications seem to me quite extraordinary. I mean, there's a thing here that apparently the average soldier going into battle carries 16 pounds of batteries in his backpack. And graphene batteries can be made much lighter. That's been a success, hasn't it? Graphene-related batteries. They last longer than lithium. And
you know, I'm not an industrialist or property developer. My Nobel Prize was for physics, not for business. This kind of questioning, okay, I accept, as well as being called Russian, I accept these kind of questions about, but it always reminds me a story, because there are some policy makers from research councils and so on. The story goes on. Once I was on a boat trip watching dolphins, and dolphins, wild animals, they don't like humans. No one likes humans, okay, but that was some kind of a strange accident. They came close to the boat and were looking for a human touch, okay? They allowed people to lean over the boat and go and touch them. I have swam with dolphins and so on, and it was a very extraordinary moment, and I couldn't believe this. You probably imagine that everyone of clients on this boat were at awe. It was a romantic moment. And then someone behind shouts, "Ma'am, can we eat that?" So we are still having this romantic moment with this new class of materials. We discovered graphene is one of them. We try to enjoy this moment, and then people come and saying, okay, what this material is good for? When our goodies would coming out, okay, yes. So that's John's question, okay, but I understand this question. So typically it takes 20 to 40 years for a material to go from an academic lab to industry. The same happens with medicine, no different from this aluminium, the material without which we can't possibly live. It took about 70 years before people find something useful out of this material. Everyone was saying, oh, wonder material, so light and strong and so on. What can we do with this material? So it takes time before everything diffuses into consumer products. With graphene, surprisingly, it's happening very, very fast. 5 years ago, there was just wishful thinking. These days, production problems, graphene can be done in square meters, in metric tons, no problems. I think the production goes, okay, thousands, many thousand tons per year. People try this material in a second-tier applications, trying to a bit this, put material into batteries. It's improved a battery performance by a couple of %, but at few pennies. That's a progress. They add it to paint. Paint becomes a bit cheaper, and at the same time, it becomes more robust with respect to environment. They put it into tires. That might be the next big story. Tires becomes more durable because they conduct heat better. And this kind of dirty first applications are coming around very, very fast. There are tens of companies around the world which are already selling graphene within their products. Sometimes they call graphene something which is more the salesman trick, but the material is there.
The thing is that that's, again, proof of principle, isn't it? That if it works a little bit, surely it's going to be a bit like Moore's law, as transistors get smaller and smaller, so that graphene gets
No,
smaller.
it's more than that. It's not just proof of principle. We're doing proof of principle, but remember, we are living in the society where there are big industries, and there is a pressure on those big industries to generate profits, and they are busy with generating profits. They have no time for tinkering. They are responsible to shareholders, and etc., etc. So
I think, as a member of the public, you often get bored when you read in the papers that some amazing scientific breakthroughs taken place, which means your mobile phone will work faster and you'll be able to play games more often than you were able to before.
But it requires a lot of capital investment, and capital investment never goes into some... this is why technologies called disruptive technologies, because they disrupt normal life of industries. So, and no one will give $1 billion to bring, maybe Chinese government only to, they gave $1 billion probably altogether to bring this production to the market, but in principle it takes a long time. When you get a small success, there is a feedback mechanism, companies going bigger, production improves. So these first-tier companies, some of them got busted because they didn't have enough customers. Now they have customers because customers selling something, and thus they try to improve the quality and so on. So it's a very complex feedback mechanism. We are living in industry. We do not really realize how difficult it's to cross this bridge between academia and industry. There is no straight line. It's essentially a diffusion motion from our bank to the industry.
Well, my brother's a scientist. He's a geneticist, and every time he comes across something interesting and it has a commercial application, he's bored. He's not interested in that. He likes the science. But the thing about the applications of graphene, one particular interesting one is that it's a sort of perfect membrane, isn't it? It's impermeable to even helium in certain circumstances. So
that's correct. It's absolutely impermeable.
The upshot is that the possibility is this is going to be used for water desalination, and if it does that, it's going to solve an awful lot of lives around the world, not just from drought and dirty water, but from wars, because there's going to be water wars, the next big thing. So it has these applications which are more than just, commercial fripperies, really. Or
You know,
potentially does.
you know, John, given an examples, even such big examples like desalination and etc., which may or may not be turn out to be true, it doesn't do justice to graphene. You really have to paint a bigger picture. 10, 15 years ago, we were not aware about a whole class of materials, which are one atom or one molecule thick, was that they could exist. We were not aware. It's a new class of materials. Graphene is one of them. When we talk about graphene, it's a shorthand for many other materials which are similar, different in properties. They could be insulators, they could be conductors, semiconductors.
You were saying last night you should really people call them graphenes now, even though they're not.
Yeah, people call them two-dimensional materials.
Like plastics, but like plastic, there's more than one kind of plastic.
Yeah, it's like plastics. There are many kinds of plastic. So we have a new class of materials. And now, after finding out that this material is not only thinniness is one of the properties. It doesn't matter. It won't be good. But those materials are really different from what we know from the bulk materials, and that makes this class of materials, it's not only extraordinary, we try to incorporate all those materials in our human's toolbox and tinker with these materials. So it's not a blip on your screen. We are just, whether you like graphene or hate graphene, I personally hate it. I had enough of this material, but it's a part of my toolbox as a scientist. It's becoming a part of toolbox of industry, and this continues to happen. And the human progress has been dotted with using different materials, from stones to bronze to iron to plastics to silicon. Now we are probably at the beginning of the age of two-dimensional materials. It's not an exaggeration. Everyone who is working in this kind of area knows that it's inevitable.
That's amazing. So Stone Age, Bronze Age, Iron Age, Steam Age, Graphene Age.
No, it's not graphene. It's two-dimensional materials.
Well, no, but I mean,
you can call it.
But you've discovered a principle by, it's applying a way of looking at the world to more generally.
Yeah, when you say you discover, I think there is a little bit feeling because it's your baby. You try to sell it higher than it is. Okay, it's not. I'm trying to say it. It's what people who are dealing with this kind of materials. They know that it has come inevitable. And personally, I think if I wouldn't discover it or bring attention to this material, I don't know how many years, maybe 2, maybe 5 years, but someone else, it's inevitable was that we eventually start using this material. It's just a part of the progress. I was just a little bit quicker and a little bit more lucky than my competitors.
Well, I can understand, in showbiz, people get tired with doing a certain thing. People still say to John Cleese, "Oh, Fawlty Towers, what a great show." And he says, that was like 40 years ago. I've done other things since. But nobody else, I can understand why you might be bored with graphene because you've lived with it for so long. But I find it a very optimistic thing. I think that the sense of applications gives a sense of the future, which is not present in other areas of life, like politics, for example.
I'm a scientist, and scientifically graphene more or less done. It still brings surprises, but it's done. That's it. Now it's in the hands of industry and applications and so on. So,
well, how about the pure science?
I'm using this one. I'm using this very intensively. So I'm kind of, when you are doing graphene, essentially I'm no longer doing graphene. That's a little bit where my irritation comes about graphene, because I'm not really doing graphene.
So where are you now? What interests you now? What are you passionate about now? What are you exploring?
I probably have a slide about this one. Okay, yeah. Those random collection of slides, I didn't really.
Do you have any hexagonal boron nitride?
Yeah. So essentially, we know that graphene is not alone, that it has many sisters and brothers. Our group in Manchester was one of the first who had a look at different materials. Some of those are familiar. There is boron nitride, which is sometimes called white graphene. There is mica, of course, you know that mica, but there are many layered materials which you can do the same trick. Originally, the trick is done in the same way using Scotch tape. It's very popular among scientists for making proof of concept, because if you like to scale up, you need to know what to scale up. So we get hundreds, probably a couple of hundreds materials. I have a long list, probably several dozens of those which we have. And this is, if you wish, graphene 2.0, not graphene 1.0, which we studied before. It's a new class, and people intensively looking what is interesting about these materials. What we have done about 3-4 years ago, we went further. We start doing graphene 3.0. And imagine that when you get those materials, you can imagine you're doing something like that. And essentially, what we do, we disassemble materials which are available into individual atomic planes, and then try to assemble them back into a designer sequence with designer properties which we're trying to guess what it be. So it's still far for any applications. People still dealing with graphene. We're looking for new phenomena and new properties within this area of research.
So in terms of, I pretty much guarantee that any 12-year-old who's heard of graphene and the related studies gets all excited about science, because this is a thing in this country, isn't it? And not enough people want to do physics and maths. How do you think we can help them do it? And I think graphene's a very good way of, it's because of the solidity of it, you know, the practicality that you can make, or potentially make everything from waterproof bricks to exoskeletons to artificial skin. I think that's very exciting, because a lot of people of whom it took, I was in my 40s before I understood what was interesting about science. It's often very badly taught, because people often, I remember talking to a guy, he was professor of education at the University of Buckingham, and I was saying that physics for most people, unless you're that way inclined, unless you're a natural mathematician, physics is hard to understand and hard to see why it's interesting. And he said, we know why physics is badly taught. I said, do we? He said, yes, it's because physicists hate children. They find them annoying because they don't conform to any laws. They run about like sort of Brownian motion. And this is a thing that obviously doing QI, this really interests me. How can we get kids, particularly, Brian Cox, I think, has done some amazing work on television, to make science accessible and beautiful and strange and mysterious, and he has changed that perception, I think. And I'm interested in how we can, you know, there are great popularizers of science writing, for example, but how, I mean, you write very clearly, Andre. Your stuff is a joy to read, quite difficult papers, but you can still follow the story. There should be more of that, don't you think?
I think there are two problems with education, with the lack of young people being interested in science. One, we live in this populist culture with social media and etc. And people do not much appreciate merit. They're more focused on personalities, whether it's TV personalities or something like that. You mentioned Brian Cox doing an amazing thing, but more people know what her name was, Jordan than Brian Cox. So people are obsessed with the cult of personalities, with the Big Brother. So meritocracy gradually disappears in our society, being substituted by cries for Pan and Kirkensas bread and circuses. I'm afraid I'm not a politician. I'm not sure what to do about this. This is not only UK problem. This is the general problem of the modern society that meritocracy suffers. But
it's partly, I spent 15 years doing this show, QI, trying to take difficult subjects and make them entertaining, and it may get laughed at by serious scientists and historians, but again, it gets people interested. And somebody once said, all you need to do to educate a child is to teach them to read. Everything else is brainwashing. That really, all the things that you and I have ever learned, we've learned for ourselves, haven't we? When you're told to learn something, that's not the way anyone learns from a language as a child onwards. You really learn by doing it and by being interested, and that's the first difficulty, get people interested. And, it's not, some people are better communicators than they are scientists and vice versa.
Well, I know, John, that you are passionate about education and QI, and I leave this subject to you, okay, because, education has always been tough for me too, because I separate students into two kinds of personalities, those into which it's worth investing time and those which are not, okay? So
So I was just we're gonna have a few questions, we've nearly run out of time, but I just want to say T.S. Eliot won the Nobel Prize for Literature, as you may know, in 1948, after which he said, "The Nobel is a ticket to one's funeral. Nobody has ever done anything after they got one." Now, you don't strike me like way, Andre. I think you've got a whole new lease of life. You seem to be herring off into the distance, all these new ideas.
Yeah, there are pressures, and remember, many people get Nobel Prize when they're relatively old, in 70s, 80s, okay. I didn't reach this age yet, okay, trying to sleep on your laurels. So, but I take it's easier. We live in the society. We try to occupy our life, making them busy. And if you have done for 40 years professionally doing research, you accumulated so much inertia that you don't know what else to do if you're trying to think with politics or whatever else. It's not as interesting. You're not professional, so you try to be a part of society, contribute as much as possible into this society. So your mentality, because you're a human being, a social animal, it forces you to continue running and running. And I'm sure the same happening with you, John, okay? Maybe it's not the Blackadder goes academia. I try to persuade John to make something like intermediate between the Big Bang theory and Blackadder. I can only imagine how popular it could be in science. So you probably wouldn't like to do this, but at the same time, you're also busy with many things. Continue with being very active.
I just want to ask you one last question, Andre. What achievement do you value more, your Nobel Prize, your knighthood, or your Manchester University car park pass?
Yeah, it's a rhetorical question, of course, because especially car parking, it came as on the back of the Nobel Prize, okay? Our president and the chairman of this conference, Nancy, is there. She knows that the story when the news about the same day the Nobel Prize was announced, she asked me, "What do you want?" And I said, "I would like to have a car park next to the building."
Ladies and gentlemen, Andre Geim.